Jai Hind and welcome to all. Myself Shiwani from Applied Science and Humanities Department in Ajay Kumar Garg Engineering College will deliver a lecture on Nernst equation and its application, and it is a topic of Unit 3 Electrochemistry. And the references which I have preferred is from Jain and Jain Engineering Chemistry, from Shashi Chawla, and since the numericals are on basic concept, so I took the numerical from this Baiju site or jntu.ac.in. So, in previous lecture I have discussed that the metal which have more reduction potential, it will act as a cathode, that is its reducing tendency will be more. So, here if we take the standard reduction potential and if we took from this lithium, cesium this, so this is the increasing order of reduction potential and up to hydrogen, and since hydrogen it is very good because reduction potential or oxidation potential 0. So, this hydrogen it has 0 oxidation or reduction whatever we want, but since this is a reduction reaction, so we can say reduction potential, and the minus 3.05 it is the least value and this is the increasing order and this value. So, in this table we see that the higher position in table, it means it will basically likely to act in reducing manner, and or very simple we can say if the reduction potential is high. Reduction potential is high means it's a reducting tendency it will be more, that is that compound or that metal it will reduced, and when it will reduce, then definitely other will oxidize. So, it will be good oxidizing agent. So, higher the position in electrochemical series means very good reducing manner. So, in this case we can easily say that F2 it is a stronger oxidant than Ag plus, or copper plus 2 it is a weaker oxidant than cesium or selenium Ce4 plus. And the lower value in table means it has least reduction potential. So, least reduction potential, that is greater tendency to be oxidized. So, it is a reducing agent or reductant. So, I think do not be confused in this term, but remember like this, suppose A and B, and A has reduction potential minus 4 A has reduction potential let suppose minus 2.0, and suppose B has reduction potential minus 0.5. So, since this value is high, so B, the reduction of B will occur. So, B will act as a cathode and A definitely will act as a anode. So, now suppose in this case Sn4 plus 2 electron which will give you Sn plus 2 this, and Ce plus 3 which will give you Ce4 plus 1 electron, this is gain. So, it is the reduction reaction, and this is lose. So, it is the oxidation reaction. So, both basically, now in this case both are in reduction form, and if we check the reduction potential, the reduction potential of Ce is more. So, the reduction of Ce will take place and oxidation of Sn will take place. Now, come to the next point, which is a Nernst equation. So, first question which is what is Nernst equation? So, this equation is used to calculate cell potential of electrochemical cell at a given temperature, pressure or reactant concentration. So, we can say that this Nernst equation is useful to calculate electrode potential at various concentration, and this equation it was introduced by German chemist W.H. Nernst. So, let us consider a half cell reaction, and suppose this half cell reaction is Mn plus n electron which is Mn. So, where M is metal and this is the reduction reaction. So, in this case the work done in the movement of the electron, the work done it will be W reduction, which will give you NFE, and where E is the reduction potential. Now, the change in Gibbs free energy, and which is an indication of spontaneity, and it is also equal to the maximum work other than volume expansion which is done in the process. So, the combining work done and the Gibbs free energy, we can say that W is equal to NFE and delta G is equal to minus NFE. So, we can say the delta G is equal to minus W, and which is equal to this. Now, since for a reversible reaction we know that delta G is equal to, and which is a we can say want half isotherm. So, delta G is equal to delta G naught plus RT ln K, K or Q. So, K basically equilibrium constant and Q is the reaction coefficient, which is the ratio of product to ratio of reactant. So, in this case delta G is the Gibbs free energy of the cell and delta G naught is the standard Gibbs free energy. Now, for this reaction Mn plus N electron, which will give you M. So, in this case put the value of delta G, which is equal to minus NFE. So, minus NFE, since the reduction reaction is there, so E red is equal to minus NFE naught, E naught is the reduction potential at a standard condition, plus RT ln Q, Q is the product divided by concentration of reactant. So, M upon concentration of M upon concentration of Mn plus. The concentration of solid is always taken as 1. So, it is 1. So, what will be the value? The value will be minus NFE is equal to minus NFE naught plus R is a 8.314 and ln is the basically base E, and when we put this ln at base 10, then we can say 2.303 log. So, minus NFE, it will be equal to minus NF E naught plus 2.303 into 8.314 at 25 degrees centigrade, that is 298 Kelvin, divided by N, and F is and here sorry, no need to write here. So, 2.303 R 8.314 T 298 and log of 1 upon Mn plus here, and when we divide the overall from the minus NF, then it will become E is equal to E naught minus 2.303 into 8.314 into 298 divided by N is the number of electrons involved in this reaction, and multiply by 96500, which is 1 Faraday. 1 Faraday is equal to this, and log of 1 upon Mn plus. So, if we solve this, then 2.303 into this value come minus 0.0591 upon N log of 1 upon N plus, or we can say log of product upon reactant, or K or Q. So, 1 upon Mn plus. This is the Nernst equation for half cell, and this half cell is reduction. Now, for a reversible reaction, let the reaction is AA plus BB, which will give you CC plus DD. Now, for this reaction, the Nernst equation, it will be E is equal to E naught minus 0.0591 divided by N, N is the number of electrons, log of concentration of product upon concentration of reactant. Now, the products are C and D, and the mole of C is C. So, C to the power C, or we can say C right C side C times, and D to the power D divided by A to the power A into B to the power B. So, this is the Nernst equation for a reversible reaction. Now, application of Nernst equation. So, we will discuss application one by one with one numerical. The first application of Nernst equation, it is used to calculate the electrode reduction or oxidation potential at any conditions and the effect of electrolyte concentration on electrode potential. And we can calculate this since we want to calculate reduction and oxidation. So, it is for half cell reaction. Suppose the problem is the zinc electrode is placed in 0.1 molar solution of its, which is ZnSO4 at standard, that is 25 degree centigrade. So, calculate the cell potential of this electrode by assuming that during reaction 20% dissociation take place and the reduction potential of zinc, which is minus 0.76. Now, this is the half reaction, and since reduction potential, if we write reduction reaction, then we have to take reduction potential and at a standard condition and we calculate E reduction. And suppose we write the oxidation reaction, then instead of this reduction potential we have to put oxidation, which is plus 0.76, and we calculate oxidation potential. So, here let us take the reaction Zn plus 2 plus 2 electron, which will give you Zn solid. And since 20% dissociation take place, so after dissociation what will be the concentration of Zn plus 2? The concentration of Zn plus 2 is equal to 0.1 20% and which is 20 by 100. So, it will become 0.02 molar. Now, from the Nernst equation, half reaction, so E reduction is equal to E naught reduction minus 0.0591 upon N, since N is 2 in this, from this reaction, log of product upon reactant. The product is zinc solid and the reactant is Zn plus 2. The reduction potential of zinc, which is given, is minus 0.76 minus 0.0591 upon 2 log of solid 1, and the after dissociation the percentage of zinc plus 2 is 0.02. Now, when we calculate this, since this value is 1 upon 0.02, so it will come in plus. So, here 0.76 plus 0.05 approximately, and which is equal to 0.81 volt. So, this is the answer, 0.81 volt. So, this is the first application we can calculate reduction potential or oxidation potential at any for any condition this. Now, second application is finding the feasibility of combination of such single electrodes to produce electric potential, or we can say we can calculate the potential under standard or non-standard condition. Standard condition means if E is plus, that is the which have less reduction potential, it will act as anode or definitely other as cathode. But suppose non-standard condition is given, then we can calculate electrode potential with the help of this Nernst equation. For example, in this case, calculate the electrode potential of electrochemical cell and cell is given. We know that the reduction potential of hydrogen is 0 and the reduction potential of copper is 0.34. Now, in this condition, if we consider the value of reduction potential, and since the reduction potential of copper is more, so it should act as a cathode. But the cell is given, it means this cell is at non-standard condition, because in this case this copper, it acts as an anode, is acting as an anode, and this as a cathode. So, in this case we can find the electrode potential. The Nernst equation is E is equal to again E cell is equal to E naught cell minus 0.0591 upon n log of concentration of product divided by concentration of reactant. So, in this case, if the cell is given, so we have to take this condition. So, copper, which will give you copper plus 2 electron, because oxidation act as anode, and the concentration of copper plus 2 is 0.5. Now, the second reaction with this hydrogen electrode, it will be 2H plus 2 electron, because reduction, so it will give you H2. Now, the reaction for product and reactant, it will be Cu plus 2H plus, which will give you Cu plus 2 plus H2. So, if we write this chemical reaction, we can easily find which is the product and which is the reactant. So, in this case, E naught cell is E cathode minus E anode, but the condition is both are in reduction form. So, cathode is here from this cell equation and anode is this. So, we can write 0 minus 0.34 minus 0.0591 upon number of electrons involved in this reaction is 2 log of product. We can easily say these two are products. So, copper plus 2 into H2 divided by copper and H plus 2 ion. So, we can write 2 times or H plus square. Now, here the concentration of copper plus 2 is 0.5. Hydrogen is in gas form. So, we took the pressure and pressure here is mentioned 0.95 atmosphere. Copper solid 1 and H plus ion concentration is 0.01. So, when we put the value of all, so it is minus 0.34 minus 0.0591 upon 2 log of 0.05 into 0.95 divided by 1 into 0.01 square. And when we solve this, we get E cell 0.449, this with negative sign. So, E cell negative means delta G positive, and delta G positive means reaction is non-spontaneous. It means we required additional energy for this reaction here to basically for this formation of this reaction or this type of cell. Now, another application is it is used to calculate or to find the unknown concentration of one of the ionic species in cell. Suppose this cell ions are there, whether it is in a reduction reaction or oxidation reaction. So, if concentration is not given, we can find this. For example, the copper plus 2 ion concentration in a copper silver electrode is 0.1 and reduction potential of both are given, even cell potential is given. So, find the silver ion concentration. Now, here cell is not given. So, first we have to find which will act as a anode or other which will act as a cathode. So, in this case we compare the reduction potential of both, and since the reduction potential of silver is 0.8, which is more than 0.34. So, this will act as a cathode and copper will act as a anode. So, what will be the reaction? The reaction will be copper, which will give you copper plus 2 electron, that is anode, and second reaction will be directly we can write 2 Ag plus 2 electron, which will give you 2 Ag. Now, overall reaction, and especially when we have to find what is the reactant and what is the product. So, it is the simplest way to find the reactant as well as product. So, 2 Ag plus Cu plus 2. Now, E cell is equal to E naught cell minus 0.0591 upon N for this reaction, N is 2 log of product upon reactant. Now, the product is Ag square Cu plus 2 divided by Cu and Ag plus square. Now, E cell is given and which is 0.422 and E naught cell cathode minus anode, and cathode is silver, anode is this. So, we can say 0.8, 0.8 minus 0.34 minus 0.0591 upon 2 log of solid 1, copper plus 2, concentration is 0.1 divided by copper solid is 1, and we have to find the silver ion concentration, this. Now, we can solve this and find the concentration of Ag plus, and when we solve this, so it is 0.2422 and 0.8 minus 0.34, which will be 0.46 minus 0.0591 upon 2, which is 0.0296, and log of its concentration is 0.1 divided by Ag plus square. So, which is 0.1 log of 1 by 10, which is minus 1, minus 2 log Ag plus, and then minus 2 log Ag plus, it will be 2.283, that is log Ag plus is equal to minus divided by 2, which is 1.141. So, Ag plus will be anti-log of this, and which is 0.0722. So, the answer is 0.0722. So, we can find the unknown concentration or concentration of ionic species. Now, another application is to find the pH of the solution or electrolyte in hydrogen electrode. So, in hydrogen electrode, when we pass the H2 gas at atmospheric pressure, generally at a standard condition, so the solution which is taken is we can find the pH of this solution, and pH, we know that pH is equal to minus log H plus. So, we can easily find. The question is the EMF of cell measured by means of hydrogen electrode against saturated calomel electrode at 298 Kelvin is 0.4188, and if the pressure of hydrogen was maintained at 1 atmosphere, then calculate the pH of the solution, and the potential of reference calomel electrode is 0.2415. So, in this case, if we want to write the cell reaction, so it will be H2 and which is 1 atmospheric pressure, H plus, and we have to find this H plus concentration. So, we can find pH. So, aqueous we can write PT. Now, salt bridge KCl and then Hg2Cl2 and Hg. This is the simple cell reaction, and what will be the chemical reaction? H2, which will give you 2H plus plus 2 electron. This is at anode, and the reaction Hg2Cl2 which will give you and plus 2 electron, and which will give you 2 Hg plus 2 Cl minus. So, when its E cell is E oxide is 0, and here the potential of this is given, which is 0.2415. So, E cell will be, we can find, and when we find the pH, for this we can say E cell is equal to 0 minus 0.0591 upon 2 log of H plus square and then upon H2, and minus log H plus is equal to pH. So, we can say 0.0591 pH, this. and we know that E cell is equal to E cathode minus E anode. E cathode is 0.2415, E anode is this, and E cell is equal to 0.4188. So, the pH it will be E minus E reference, that is E cathode divided by 0.0591, and if we solve this, so we can say basically let this 0.4188 is equal to 0.2145 minus 0.0591 pH, and minus minus here minus minus, then and we solve this, it will be, and oxidation, then this will be minus. So, the reaction we can say here. So, when we solve this and this value it come in positive, so it will be 3. Now, next is, it is again used to determine K. So, direct we can do this question. So, in this K, E cell is given, for this at equilibrium, when we find the equilibrium constant, then we can say at equilibrium E cell is equal to 0, then E naught cell it will be equal to RT upon NF ln equilibrium constant log K, and 2.303 is also here. So, that is E naught is equal to 0.0591 upon N log of K. So, from this we can find the log K or K, where K is the equilibrium constant. Now, limitations. So, first limitation, in a very dilute solution, the activity of an ion is close to infinity and it can be expressed in terms of ion concentration. However, for solution having high concentration, the ion concentration is not equal to ion activity. So, in this order, if we Nernst equation is used, so the experimental measurement must also be conducted for known to find the true activity of the ion. And the another shortcoming of this equation is that it cannot be used to measure cell potential when there is a current flowing through the electrode, because the flow of current it affects the activity of ion on the surface of the electrode, and also additional factors such as resistive loss and over potential it must be considered when there is a current flowing through the electrode. So, this is the derivation and problems and limitation of Nernst equation. Thank you.